So we can start our live session in like 2-3 minutes. So good evening, everyone. Welcome to the course Fabrication Techniques for MEMS-based Sensors from the Clinical Perspective. Today we are having our week 7 live interaction session, and I'm the course TA, Rayan Jasma. So we'll be having this course every week on Monday from 6 p.m. to 8 p.m. And like this is the link of the YouTube channel where we will have the recorded videos and the slide content which is uploaded. Okay. So we can start our session for that 1 minute. So first, now let us start with problem 1. For the measurement method of mechanical properties of tissues, what are the methods or tools or equipment among the following are used? In this question, we have to answer what are we using to measure the mechanical properties of a tissue. So option A is micromanipulator, B is AFM, C is FESEM, D is stereo microscope, and E is interdigitated electrodes. So which one is the correct answer? Which one is the correct answer? Okay. So before let me tell what each of these components are. Then like you may have a better understanding of what may be the correct answer. So first is we have AFM. AFM is atomic force microscopy, or it is also called as scanning force microscopy. How it generates images that it scans a cantilever over the surface of the sample. So this cantilever will have some very sharp tip at the edge. So this will come in contact with the surface. So some amount of like feedback voltage will be given to this cantilever in order to make it come in contact with the surface. Then like we'll be shining a laser at the tip of the cantilever. The amount of light that is reflected from this tip will be sensed by some position sensitive detector. So this will give us like what is the height of the cantilever, meaning like how much the cantilever is bent. So with that, we'll be able to know like what kind of terrain or what the sample has. There are many applications for AFM. One of them is like you can use to do surface mapping. It means you can find out what is the profile, what kind of terrain is the surface of a sample, and so on. You can also um, manipulate any sample. So this cantilever is generally actuated by using some piezo actuation scheme. Uh, like it will be made in contact by applying suitable amount of piezo voltage. You can make the cantilever apply some suitable amount of force on the uh, so by applying suitable amount of voltage, on the cantilever uh, by applying suitable amount of voltage to the cantilever using a piezo scheme. You can make sure that the cantilever is in contact with the surface, then you can map the displacement. So other than this surface mapping, we can also like use this like make this cantilever bend in a particular way to apply some particular force on a sample. Like you can use it to stimulate some cells and so on. So that is AFM. So this is how the tip will look like. Okay, it is kind of pyramidal kind of structure. Okay, next is FESEM. FESEM is like full form is field emission scanning electron microscopy. So FESEM is field emission scanning electron microscopy, and it is like similar to SEM. It will use electron beams in order to create some high resolution images. So it is generally used for imaging sample. This you can use for measuring the surface topography or interact with the surface. So stereo microscope is just a like a normal microscope, which is used for seeing any optical images. So here you can see a stereo microscope. Then like micro manipulator is something that that is used for like precise movements. So here you can see some like three different knobs, right? So we have knobs for X, Y, Z. So we can move precisely in X, Y, and Z motion. So this is generally used for like precision work, for movements which are not possible by the human hand. And at the edge of this micro manipulator, we can have like probes, micro pipette, or electrode, or any assembly which we want to move like very precisely. Then we know interdigitated electrodes, which we have seen in our the lesson many times. So interdigitated electrodes are just electrodes that have like, so digits means fingers. So they are just closely spaced fingers which are arranged in some interleaving fashion. Like they are also called as comb electrodes. Then these can be used to measure any like electrical properties of the cells, like impedance and so on. So what do you think is the correct answer? So among these options, which option do you think you can use to apply? Uh, so here what you want to measure is mechanical properties, right? And you would have learned in previous lessons that the mechanical property that we measure is the stiffness. In order to measure the stiffness of the tissue, what we will do is we will prod the tissue, and then like we will from the response of that we will measure how much stiff the tissue is. So in order to apply some kind of force to the tissue, like which of these options do you think you can give? FEACM is like for, it's for viewing images, so we cannot use this. Interdigitated electrode is mainly used for measuring the electrical properties, so this also is no wrong. Stereo microscope is also wrong. So in AFM, we have a tip at the edge of the cantilever. By using this tip, we can like give some amount of force to the tissue, and also like the cantilever will be connected to some piezo electric actuation mechanism, so we can control how much force we are giving to the tissue as well. So AFM is correct answer. And in micro manipulator, you can like do precise movement. So if you have some kind of structure like indenter, uh, which is similar to the normal one. So if you have some indent, something like this, can not exactly a cantilever, but something which is having a tip which will give some amount of force to the tissue that is placed underneath. You can use this also to study the elasticity of the tissue. So the correct answer is option A, micromanipulator, and B, AFM. So by using these two techniques, these two tools, you can give some amount of force to the tissue. By giving some force to the tissue, you can study the mechanical properties of the tissue. Is this clear? Okay. So now let us move on to the next question. Consider the statement elasticity of normal epithelial tissue is less than the that of the cancerous epithelial tissue. This statement is true or false. So this is kind of related to the previous question. So we know that the elasticity of normal tissue is different from that of the cancerous tissue. But whether the normal tissue is having lower elasticity than that of the cancer tissue or not. So which one is the correct answer? So this is for epithelial tissue. So what happens when somebody is having cancer? Like cancer causes some change in the normal cell structure and organization. It will cause some change in the cell structure and organization. So what? So when somebody is having cancer, they will have like more disorganization in their tissue. So what happens as a result of this is that the stiffness of the cancerous epithelial tissue decreases. So for different types of tissues, the elasticity like may be different from that of the normal cell. Like in some kinds of cancer, it may be there is a chance that the elasticity may be higher than that of the normal cell. But in the case of epithelial tissue, it has been found that the cancerous epithelial tissue has a low stiffness compared to that of the normal epithelial tissue. So in this question, what it is mentioned is that normal epithelial tissue is having less elasticity than cancer. So this is false. The correct answer is false. Okay. So one reason is that there is something called as cytoskeletal filament in a cell. So once like when the cancer like occurs for a patient, the cytoskeletal filaments like sometimes they get degraded. So because of that, the stiffness of the cell gets affected. So that is one of the reasons that they say that is causing the change in the stiffness of the tissue. And this change in the elasticity of a cancerous cell is used as one of the biomarkers for early diagnosis of the metastatic potential. So like this is used for diagnosis of cancer. The elasticity of the tissue is used as a biomarker in order to find out whether a person has a cancer or not. Is this clear? Then let us move on to the next question. For the experiment to understand the electrical properties of tissues to predict whether the tissue is benign or malignant, which of the electrical parameters of the tissue are plotted and reported to predict the state of the tissue? Option A, resistance and log of phase angle. Option B, impedivity and phase angle. Option C, log of impedance and phase angle. Option D, log of impedance and log of phase angle. So which one is the correct answer? So here what we are doing is we are trying to study the electrical properties of the tissue in order to find whether it is cancer or not. And what kind of electrical property are we measuring? Uh, any guesses regarding the correct answer? So we know that we can measure in another example where we had mentioned about using the electrical properties of cancerous tissue in order to diagnose cancer. The electrical property that we are using to study is impedance, right? So the correct answer is log of impedance and phase angle. So let me explain what this means. So while measuring, let's say yes. So let's say I'm measuring the uh, electrical property of a tissue. What generally people do when they measure is that they measure the impedance against frequency. So this impedance is it is the real part of resistance, real part which is a resistance plus the imaginary part of resistance which is called as reactance. This will include the inductance as well as the capacitive components. So the total will be imaginary and which is like complex number. So complex numbers we can represent them as real plus imaginary, or we can also represent complex numbers as in magnitude and phase form. So here we are writing when we are taking log of impedance, we are taking the magnitude. So magnitude of impedance, and this is represented in log form. So the unit for this will be in dB decibel. Then in order to find, we will also plot the phase information. So this will be phase of impedance, and this is plotted at different frequencies. Because the impedance will be like the imaginary, if the impedance is having imaginary term, then that will be a function of frequency. So we are plotting it against frequency. Is this clear? So the correct answer for this question is we are plotting log of impedance and phase angle versus frequency. Okay, we cannot plot log of phase angle. There is no it's not correct. And phase log of impedance is generally it can be positive, negative. Uh, Depending on the value of the impedance. Okay, it can also be 0, and phase angle is generally it will vary between -180 to +180, or it can be 0 to 360 depending on that. Okay, so now let's move on to the next problem. Which of the following breast lesions are non-invasive malignancies? Yeah. A. Invasive lobular carcinoma. B. Lobular carcinoma in situ. C. Ductal carcinoma in situ. D. B and C. So which is the correct answer? So this question is regarding to breast cancer. So which are non-invasive malignancies? Okay. So what is malignancy? So here malignancy means the cancer cells which are having the ability to spread to other sites of the body or invade nearby cells or tissues. Okay. Non-invasive means that it will not spread beyond the tissue in which it has originated. So let's say if the cancer cell has started in breast, it will not spread beyond the breast. Okay. So which of these following options are non-invasive malignancy? Means they will spread, but they will not spread beyond the region by which they start. Okay, like you can see the clue in the options itself. So in the first option we have invasive, right? Invasive means it will spread to other organs. So this is wrong. And then in option B we have lobular carcinoma in situ. And so lobular carcinoma means it is cancer in the lobe region of the breast, and ductal carcinoma is cancer in the duct region of the breast. What does this in situ mean? In situ is a Latin phrase that means on site or in place. So by this itself, we can say that these two cancerous, like these two cancers will be like they will not spread beyond the tissue in which they originate. Okay. So the correct answer is option D, B, and C. So in problem 4, we have which of the following breast lesions are non-invasive malignancies? The correct answer is option B and C. The clue is given here, like inside to. Inside to means it will not, it is inside or on place. That means it does not spread beyond the place in which it originates. Is this clear? Now let's move on to the next question. Problem 5. Base resistance value of chrome gold IDE structure with a spacing of 10 microns and 50 microns are X ohm and Y ohm respectively. If the spacing is increased, how will it affect the base resistance? Option A, base resistance increases. Option B, no change in base resistance. Option C, base resistance decreases. Option D, data insufficient. Okay. So in this problem, we are having IDE structures. Okay, let's say these are our IDE structures. And what is given is that the spacing between them is mentioned. One is having a spacing of 10 microns, and the other is having a spacing of 50 micron. Okay. So this is the spacing that we are talking about. So if the spacing is increased, how will it affect the base resistance? So let's say we are not having any uh, we are not having any sample between these two IDEs. Then what will be the resistance of the IDE? The resistance of the IDE will be infinity, right? Why? This is because like between the IDEs there is no conductive path for current to flow through. So like it is like open circuit. Open circuit means we are having very high resistance. So we can say it as infinite resistance. So even if we have like if we increase the spacing, unless we have some conductive path between the two IDE structures, so between the two interdigitated electrodes, then like the resistance will not change much, right? So the correct answer is no change in base resistance, which is option B. Correct answer is no change in the base resistance. Okay. So this is problem 5. So now, is this clear? Uh, so to summarize again, here like this will increasing the gap spacing between the interdigitated electrodes will not affect our the resistance of the sample. That is because like even if we increase the spacing, there is no conductive path. We are not changing the conductive path between the two IDs, so it will not affect the base resistance of the sample because the base resistance is already very high. When you are increasing, it does not change much. Okay. Is this clear? Now let's move on to the next question. Problem 6. in the experiment that measures the electrical properties of the tissue, evaluate whether the following statement is true or false. For the equivalent circuit representation for the experiment, the tissue is modeled as a resistance, and the solution it is in PBS is modeled as a combination of resistance and capacitance in parallel. So is this true or false? So when we are measuring, like how do we measure the electrical properties of a tissue? We have IDE, interdigitated electrodes. We make some, like we suspend the tissue in some kind of analyte. So in this question, PBS is an analyte in which we are suspending the tissue, and then we will keep the analyte along with the tissue between these electrodes, right? So there will be some conduction path that is formed due to the tissue and the analyte. So here, like when we are measuring, we need to measure only the electrical properties of a tissue. So we will have some kind of model which we can use in order to just extract the electrical properties of the tissue only and not the solution. So here in this question it is mentioned that we are using resistance for the tissue and the solution is modeled as a combination of resistance and capacitance. So is this correct or wrong? So in previous lectures itself, when we were talking about the electrical properties of a tissue, we always like represented it as impedance, right? A combination of resistance and capacitance. So like not just resistance. So this is false. The correct answer for this question is false. So there are various models for modeling the tissue and the solution. And in like many cases, the circuit model will depend on like what are the properties and what are the kind of interactions that are happening. So like to say in simple, the electrolyte can be modeled as a resistance if you are considering very simple model, and the tissue will be generally modeled as a combination of resistance, capacitance, and inductance. Is this clear? Now let us move on to the next problem. Problem number 7. Evaluate whether the following statement is true or false with respect to the device for evaluating the efficacy of immunotherapy devices. Okay, now let us see problem 7. Evaluate whether the following statement is true or false with respect to the device for evaluating the efficacy of immunotherapy drugs. For growing the spheroids, the cells were grown in ultra low attachment 96 well plates. Is this true or false? So this is a question from the lecture. It's a direct question. You can just answer it. So here, what spheroids we are growing? We are growing the tumor spheroid. So like anyway, once we grow the spheroids, we have to transfer the spheroid to another to the microfluidic device or something else, or to a medium. So like what we will grow is we will grow it in ultra low attachment 96 well plates. We don't want the spheroids to get attached to the like plate in which where we are growing. So the correct answer is true for this question. Okay. Now let us move on to the next question, problem 8. For the microfluidic chip for evaluating the efficacy of immunotherapy drug that was covered in the course, evaluate which of the following statements are false. Option A, the efficacy of the drug was evaluated using electrical sensing modality. Option B, the cancer cells were introduced in the form of spheroids in matrigel. So this is similar to the previous question that we have shown, that we have seen. So what is the correct answer? Okay. So like here we know that we are using electrical sensing modality in order to test the efficacy of the drug. So option A is correct. Okay. Now option B, so we just have to see which is the cancer cells were introduced in the form of spheroids that we saw in the previous question, that we are forming spheroids from the tumor cells in matrigel. So matrigel, like various kind of cells generally get attached to matrigel. So matrigel is generally used as an attachment substrate for cell culture. We don't want the cells to get attached when we are trying to like form spheroids from the cells, right? If it gets attached to the matrigel, then it will be difficult to transfer these cells to the microfluidic device. So this is false. This is true. So like here, if you are finding which of the following statement is false, option B is the correct answer. Okay, so this is false. So instead of using like matrigel, what we use is we will use that ultra low attachment plates. So these plates like they can be used to culture medium, but like the medium, whatever cells that we are get culturing will not get attached to these to the substrate. Is this clear? If it is clear, we can then move on to the next question. Okay. So now let's start with problem 9. For the microfluidic chip for evaluating the efficacy of immunotherapy drugs, which kind of spheroid among the following is used? Option A, human breast cancer cell spheroids. Option B, mouse breast cancer cell spheroids. Option C, melanoma spheroids. Option D, none of the above. So this is also a direct question. You can just answer which one is the correct one. So here we are testing the immunotherapy drug. So which kind of spheroid are we using? The correct answer is option B, which is 41 mouse breast cancer cell spheroids. Okay. So now let's move on to the next question, problem 10. How do you measure electrical impedance in electromechanical phenotyping of breast cancer using flexible MEMS? So in here we are using flexible MEMS in order to measure the electromechanical property, and how we are how are we measuring the electrical impedance using this technique. Okay, so the correct and what kind of structure are we using in order to measure the electromechanical phenotype? Like what flexible MEMS? This kind of like we are using this kind of structure, flexible MEMS structure which can be attached to some kind of let's say a manipulator. It can be attached to some cone kind of tip. Okay, and then so we'll have this cone kind of structure. Then we'll have an electrode at the bottom. In this cone, we have conductive pads, and we also have electrodes. Then we'll have the tissue in between. This cone structure is mounted on an assembly, which is controlled by some manipulator. So we can make this tip of the cone come in contact with the tissue. So once it comes in contact with the tissue, current will flow through the tissue. So we'll be applying some voltage between the cone, like the electrodes in the cone as well as the bottom electrode. By measuring the voltage by current, which will give us the impedance of the tissue, we can measure the electrical impedance. So here only thing is that we are having one electrode at the top, which is made by a flexible MEMS structure. Okay. So here you can see these are the contact pads, and these are the electrodes. This tip will make contact with the tissue. So once it makes contact with the tissue and presses against it, since we are having some electrode at the bottom, like there will be some sort of conductive path between the two. So when we apply voltage across these two electrodes, then we'll have some current flowing through the tissue, from which we can find out what is the electrical impedance of the tissue. Is this clear? Okay. So now let's move on to the next question. Problem 11. Why do you need zigzag pattern for gold electrodes for strain gauge and SU8 pillars in the EM using flexible MEMS? So EM is measurement of the electrical and mechanical property. So here for the you can see that this is a picture of the flexible MEMS device that we have for uh, measuring the electrical and mechanical property. So why do we need this kind of flexible structure? Why can't we have, sorry, why do we need this kind of zigzag pattern? Why can't we have some straight pattern of gold electrodes? What is the main reason? So this was discussed in the course again. So it's a direct question. So the correct answer is in order to avoid the stress. So since it is a flexible MEMS structure, when we are pressing across the tissue, like it will bend easily. In order to avoid the stress, we are having this kind of zigzag pattern in the electrodes. Okay. So like the zigzag pattern is to avoid the stress. Is this clear? Then we can move on to the next question. Problem 12. How do you sense mechanical property of tissue using a piezoresistive microcantilever? So in this right here you have a cantilever structure and you are having a SU8 tip. So and also here you have piezoresistor contact pads, and if you see like your piezoresistor is somewhere along this region. So first, what mechanical property are we measuring here? Here we are measuring the elasticity of the tissue, right? So how are we sensing? What we'll do? So what we will do is we'll have some indenter. Okay, this is an indenter. So that is used to apply some amount of like force to the tissue. Then here also we'll have a SU eight tip and a cantilever. So this force will get transferred to the tip of the SU eight structure. So depending on the elasticity of the tissue, like the amount of force that is transferred to the SU eight tip will vary. Okay. So like depending on how much force is transferred to the SU eight tip, the amount of bending of the cantilever will vary. Depending on the amount of bending of the cantilever, we'll have some strain generated at the fixed end. So why we are having strain generated? This is because let's say if cantilever is bending like this, here our structure is fixed. So in this region you can see like it will start to get compressed, and in the top it will start to get stretched out. Means the material will start to get stretched out at the top, and it is getting compressed at the bottom. So like there is some amount of stress that is present at the uh, regions where it is constricted. So there if we place a piezo resistor, we can measure like the change in strain will cause some change in the resistance of the piezo resistor. And by measuring like by putting this piezo resistor in a circuit called as Wheatstone bridge circuit, we can find out how much change in output voltage is coming because of this uh, bending of the cantilever. Okay. So the correct answer is stiffness is being detected when we are pressing on the tissue, the resistance of the piezo resistor will change. Okay. So one question is here in this figure, you can see that the cantilever is exact straight. In last week's lecture, we saw that like there is some generally when we have a cantilever structure and when we release it, it will not be exactly straight. It will bend either in this direction or in this direction due to so cantilever structure will not be exactly straight. It will bend either in this direction or in this direction due to the some residual stress that is present. So in order to let's say we are having a cantilever which is having SiO2, then in order to compensate the residual stress, what material can we use? Uh, what material can we use in order to compensate the stress in this cantilever, in order to make it straight? So SiO2 is a material which is having compressive stress when compared to silicon. Like if it is deposited on silicon, it will have some compressive stress. So in order to compensate for the stress, we'll deposit a material which is having tensile, inherent tensile residual stress like silicon nitride. So if we adjust the thickness of the silicon nitride and silicon dioxide accordingly, then we can compensate for the stresses so that the cantilever structure, when it is released, will be straight and it will not be bending either like this or this due to some of the residual stress that is present in it. Is this clear? Now let us move on to the next question. Problem 13. In electrical characterization of tissue using interdigitated electrodes in SU8 well, sensitivity of 10 micrometer spaced IDE is better than 30 micrometer spaced IDE. So IDE is interdigitated electrodes. And you have to say whether the statement is true or false. Okay. So let's say I'm having my first IDE like this, and my second interdigitated electrode is like this. What you have to say is that whether you are like if you are having a 10 micrometer spaced IDE versus if you are having a 30 micrometer spaced IDE, which one will have better sensitivity? So sensitivity is change in output divided by change in input. Like for a particular change in input, how much change in output you are getting. If you so these are like um, having various geometric parameters. So, like interdigitated electrode is a structure. Like there are various parameters which can be modified in order to improve the performance of the interdigitated electrode. So one is the length of the finger, which is this. This is the length of the finger. The width of the finger, this. Gap between the fingers. Number of fingers. Then thickness of IDE, interdigitated electrode. So these are some of the parameters that we have in our hand, like which we can vary in order to improve the like performance of the device. But among these parameters, only some of them will improve the sensitivity. So it has been found that like if we are changing the gap, generally as we decrease the gap between the fingers, then the sensitivity increases. So this has been found, and one of the main reason is that as we are so we are applying voltage between these two IDEs, right? Like when we are reducing the gap, so the voltage will be the same. However, like we know something called electric field, right? Electric field is voltage divided by distance. So as we reduce the gap, the amount of electric field will between these two IDEs will increase. So if the electric field increases, then the amount of current, let's say if you're having a tissue in between them, then the amount of current that is flowing will also improve. So the current density, to not just the current, the current density will actually improve if your electric field increases, and thereby since your current density is increasing, your current will also improve. So this will cause improvement in the sensitivity of your IDE structure. Okay. So, if we are using a IDE which with is having less gap compared to that of an IDE which is having more gap, then your sensitivity will improve. So the correct answer is true for this question. So generally, in literature, uh, for very small cells, they try to reduce the IDE space even smaller, like to the nanometer scale. Is this clear? I'll summarize this question once again. So here, as gap decreases, electric field increases. So as electric field increases, current density increases. So we will, which we can say that current also increases, right? So when the current flowing through the tissue increases, the sensitivity also improves. Is this clear? And also, let's say if we have more number of fingers, then your sensitivity also will improve. Like if you instead of having one array, if you're having more number of arrays. So like this. So these two pair of electrodes will form one sensor. These two pair of electrodes will form another sensor, and so on. So as you increase the number of pairs of sensors that you have, your sensitivity will also improve. So that is also another parameter which can be played with in order to improve the sensitivity of your of your ID, interdigitated electrodes. Is this clear? Now let us move on to the next question. Okay. Problem 14. What is immunotherapy? How do you test the efficacy of immunotherapy drugs? Okay. So, what is immunotherapy and how do you test whether the drugs are efficient or not? Like any drugs that are used for immunotherapy are efficient or not? How do you test that? Okay. So, compared to conventional chemotherapy, like immunotherapy is another form of cancer treatment. Uh, like from this word itself, immuno and therapy, right? So here we are using our immune system to fight cancer. So generally, our immune system will help our body to fight infections and other diseases. So what are all what does our immune system comprise of? Our immune system comprises of white blood cells and like some of the lymph system tissues, like organs and tissues. And in this therapy, we will use uh, like our immune system to fight our cells. So what happens is that uh, like instead of giving drugs like to fight which will kill the cancer cells directly, we will give some drugs to the immune cells which will make it fight the cancer cell. So generally like in immune cells we have or various types of cells, but there are one types of cells called T cells. Okay, so these T cells uh, are the ones that are generally used in the immunotherapy. And how do we test the efficiency of these immunotherapy drugs? First, we will test whether the cancerous tissue can be treated by immunotherapy or not. In order to test whether the cancer tissue is tested by immunotherapy, we look for something called as PDL1. Okay. So, like PDL1 is a type of protein that is present in the cancer cell. Uh, if you are having like PDL1, then you can use it to. Okay, so generally PDL1 is found on healthy cells. What it will do is it will stop the cells from the immune system called as T cells from attacking the healthy cells in your body. So, if your cancer cell is having this particular protein called PDL1, then your immune cells will not attack the cancer cells. So, what we will do in immunotherapy is that we will give some drugs which will activate the PDL1, means which will like reduce the amount of PDL1 or turn off the PDL1 in the cancer cells. Or in another words, we can tell it as it will inhibit this PDL1 in the cancer cells. Once this is inhibited, the T cells will start attacking the cancer cells. So by doing this, we can use our T cells in order to fight cancer. But not all cancers can be treated using immunotherapy. So for some certain types of cancers, immunotherapy is used as like a treatment mechanism, but in some cases like there are tests that are going on in order to find out whether immunotherapy is very efficient in treating the cancer or not. Yeah. So in traditional cancer therapy we either use radiation or drugs, chemotherapy, radiation or drugs, in order to kill the cancerous cell, but that also kills our healthy cells. But in the case of cancer immunotherapy, by like turning off the PDL1. So if your cancer cell is having PDL1 and if you are giving some sort of inhibit like drug in order to inhibit the PDL1 in your cancer cell, then your T cells will start attacking the cancer cells. Why this happens? This is because the PDL1 like it kind of sends a signal to your T cells not to attack the cancer cells. If there is no PDL1 in the cancer cell, then your immune cells will start attacking the cancer cells. Okay. And by measuring the PDL1, you can find out like whether you can, if you are having PDL1 in the cancer cell, then you can use it to treat using immunotherapy. Is this clear? Now let's move on to next problem. Problem 15. The method for fabricating a microfluidic chip for evaluating efficiency of immunotherapy drugs is option A, 1 mask process, option B, 2 mask process, option C, 3 mask process, option D, 4 mask process. So here you just have to tell how many masks you are going to make and what kind of device you need is a microfluidic chip in order to evaluate the efficiency. So microfluidic chip consists of like some channels through which you will flow the fluid, and also like cells suspended. You can study cells also suspended in some medium. You can study their properties or their interactions with various other cells, or you can also test the efficiency of a drug. So how many masks do we need for a microfluidic device? How many masks do we need for a microfluidic device? And what kind of material are we making the microfluidic chip? Okay. For a microfluidic device, we'll use a 1 mask process. Okay, the correct answer is option A, 1 mask process. And what are the steps in that 1 mask process? First is we will, let's say we are taking a SiO2 substrate. This is SiO2. We are having SiO2 on silicon. Then we will do spin coating using SU8, and the reason we are using SU8 is we need high aspect ratio structures. So if you want like channels which are narrow and channels which are narrow but are having like large height, then you can use SU8. So in the second step, we will expose and develop a island structure. So we'll have some kind of island structure like this using SU8. And then we will have the silicon dioxide region and then silicon. So this is after development. So after this step, what we will do is we will pour PDMS on it. So this one will act as a mold. And once you pour PDMS, like the PDMS will cover the regions. So once you peel off the PDMS, in PDMS, what you will get is this kind of structure. So it will be a kind of duplicate, means not duplicate, inverted copy of this. So what you will see is so you will have some channels and then some walls on the side. So that is what you will have in your PDMS structure. Then like to form a channel, we need some enclosed cavity. So we will bond this with glass. Like we will bond between glass and PDMS using oxygen plasma. So this also we saw in the previous live session. So these are the steps. Next, now let us move on to the next problem, which is problem 16. What is the immunomodulator used to block the PD-1 immune checkpoint on T cell? So this PD-1 is what? It is a type of protein that is present on the cancer cell. So what immunomodulator do we use in order to block this PD-1 immune checkpoint? So this is very simple. So here PD-1 is programmed cell death protein PD-1. What is the immunomodulator used to block the PD-1 immune checkpoint on T cell? So here this PD-1 is a checkpoint that is on T cell. In previous question, you saw that PDL1 is a checkpoint that is on tumor cell. So what happens is that when like this PD-1 will bind to PDL1, and this binding of PD-1 to PDL1 will prevent the T cells from killing the tumor cells. So PD-1, the full form is programmed cell death protein 1. Okay. So if we can prevent this binding of PD-1 to PDL1, then we can make the T cell attack with the tumor cells. So we are using some kind of immunomodulator, that is something to modify the immune response in order to block the PD-1 immune checkpoint. So these kind of immunomodulators, you just have to add anti in front of that immune checkpoint. So the modulator is anti-PD-1. Yeah. The correct answer is anti-PD-1. So what happens is that this like when we are giving this kind of immunomodulator, this will wake up the anti-tumor immune response, so that the T cells can target the particular cancer cells and can like try to uh, we can try to use this as a therapy for treating cancer. Is this clear? Now let's move on to the next question, problem 17. What is the technique used to detect the CD4-CD8 ratio in blood? Okay. So what's the correct answer? The correct answer is we are using some technique called flow cytometry in order to detect the CD4 by CD8 ratio in the blood. Before that, let me ask another question. Why do we need to detect the CD4 by CD8 ratio? And what does it mean? So this CD4 by CD8, it is a reflection of the immune system health. So how healthy your immune system is. So if it is greater than 1, then a person is your immune system is uh, healthy. If it is less than 1, then that means that the person is suffering from some kind of disease. Here this CD4 cells, they are also known as CD4 lymphocytes or T helper cells, also T cells. What they will do is they will stimulate other immune cells in order to bring about some immune response. Okay, so this will stimulate to bring immune response. Then CD8 is the cells which are used to fight the infection. So if your CD4 by CD8 is greater than 1, that means your cells that are used to stimulate to bring immune responses higher than your cells that are used to fight infection. That means your immune system is healthy. It means that your system is not fighting any infection currently. However, in the case of cancer and certain other diseases, what will happen is the immune system will be trying to fight some infection. So the amount of CD8 cells will be very much higher compared to that of CD4. So that means like your CD4 by CD8 count will be less. Okay. So in order to like if you are taking a blood sample, we measure like the number of CD4 cells and CD8 cells by using some technique called as flow cytometry. Okay, so here you can see the figure for flow cytometry. Like this is a basic block diagram of a flow cytometer. In this, what happens is that like we will have the cells from a sample, we'll suspend it in some medium. We will use one or more excitation lasers. Then depending on the fluorescence and other, so this laser will fall on the cells that are suspended in the medium. Depending on the fluorescence of the cells, we can like detect the different cells. So each cell will have a particular kind of fluorescence or some other optical property which can be used to differentiate between the cells. Then we'll have multiple detectors which can be used to count the cells. So generally what we will do is that um, like we will try to count how many cells are there. It's kind of an imaging technique in order to find number of cells. By counting how many CD4 cells and how many CD8 cells are there, you can find out whether a person is healthy or they are having some infection. Okay. So in this technique, you can also measure the physical properties as well as chemical properties of the cells. Is this clear? This is clear. Then we can move on to the next question. Problem 18. Why do we prefer a in vitro patient-centric dynamic platform over a static platform for testing drug efficiency? So in static platform, like we do not move the sample or anything. We just keep the sample as such. And in the case of a dynamic platform, the sample will be made to move as it is, like not exactly as in the patient, but the movement will be we'll try to stimulate the actual human body like effect on the sample. And uh, why do we prefer a in vitro patient-centric dynamic platform over a static platform? What are the main reasons for this preference? Uh, for this question, main reasons are: first is it can mimic human body conditions. Then improve accuracy in drug prediction. Customize medicine for patients, because for every one the like reaction and the conditions will be different. Then you can better understand the drug effects better. Simulate interaction between drugs. And then you can monitor responses of drugs over time. Any other questions? Any other questions? If not, we can end this session. Thank you.